Welcome to the Introduction to Organic Chemistry simulation. Today you will learn the basics of organic chemistry and how this is connected with carbon, an essential element for all life. You will understand how organic compounds can be represented and perform simple experiments to identify some functional groups. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. Click Continue to start your mission. This is your lab pad. Use the lab pad at any time to access relevant theory about the lab or additional instructions on what to do next. You can slide down the lab pad by clicking anywhere on the background. Try it out. Well done. When your lab pad is lowered, you can listen to me without having to click Continue. Now click on the corner of your lab pad to raise it. Using the lab pad is an important way to get the most out of the simulation. Do you want me to explain how it works? Perfect. Then let's get started with your first mission. Let's go check out what's wrong with Simon.
Hey. Thanks for coming by. This toothache is killing me. I hope the pills my friend gave me relieve the pain soon. She said they contain salicylic acid, and that it's an organic compound with good anti-inflammatory properties. However, I don't understand why she said it's organic. It doesn't grow in the field like carrots or cotton. I thought you could only find organic compounds in organic food or fabrics. I was thinking, since you're into chemistry, why don't you go to the lab to find out what these organic compounds are? Also, it would be nice if you can confirm that these pills are really salicylic acid. I don't want to repeat that experience with the alchemist.
I'm sure you've also had toothache and remember that it's not a fun experience. Will you be able to understand the basic chemistry of the organic compound Simon has been given and confirm that he doesn't need to worry about these pills? Pick up a lab coat from one of the lockers to get started. Interact with the lab pad for more info. What makes organic chemistry so interesting? Have a look at the screen on the wall to your right. What do these three images have in common? Interact with the lab pad to answer the question. Exactly. The backbone common to DNA, sugar, and coal is carbon. DNA is present in all living cells, and both sugar and coal are produced from living organisms too. Did you know that you are actually 18% carbon? Because carbon is the backbone element for life, the study of carbon-hydrogen-based compounds is called organic chemistry. We'll start by getting you up to speed with basic organic chemistry, before we look further into the mission from Simon. Are you ready for a fascinating journey into organic chemistry? Then let's go to the holotable in the right side of the lab. Go to holotable 2. Here you can see a methane molecule, one of the simplest organic compounds. In the 3D models, black represents carbon and white represents hydrogen. But why are carbon and hydrogen bonded in the way they are? Let's look into the bonds of carbon in this atomic animation. The carbon atom has 6 electrons. These electrons have the following orbital configuration: 1s2, 2s2, 2p2. This means that there are 2 electrons in the inner 1s subshell, 2 electrons in the 2s subshell, and 2 electrons in the 2p subshell. The 2 electrons in the 1s subshell are not of interest in organic chemistry, so we'll leave them for now. We are now looking at carbon's valence electrons, which are those that are used for forming bonds. Let's check out how they are arranged. 2 electrons are orbiting in the 2s orbital, and 1 electron is orbiting in each of the 2px and 2py orbitals. As you can see, the 2pz orbital is currently empty. Carbon normally forms 4 bonds, but here, only the 2p electrons are unpaired and available for a chemical bond. How can that be? We can get 4 unpaired electrons through an excitation of one of the 2s electrons into the unoccupied 2pz orbital. Carbon is now almost ready for forming bonds. Carbon bonds depend on the type of hybridization that takes place in the electron orbitals. Hybridization is a process where the orbitals mix to form hybrid orbitals. Let's see the different types of hybridization, starting with the most simple, the sp3 hybridization. In order to form 4 bonds with other atoms, the 2s, 2px, 2py, and 2pz mix to form 4 equal orbitals, called sp3. This is the process of hybridization. The sp3 orbitals form the 4 corners of a pyramid with triangular sides, a so-called regular tetrahedron. The angle formed between the orbitals is 109.5 degrees. With the sp3 orbitals, each occupied with a single electron, carbon can form 4 equivalent single bonds with, for example, hydrogen. These are called sigma bonds. The angle between the orbitals will determine the angles between the chemical bonds the carbon atom will make. So when forming sp3 orbitals, the angle of the bonds will be 109.5 degrees. A carbon atom can also bind to another carbon atom using a sigma bond. The rest of the sp3 orbitals can then form more sigma bonds with other compounds. For instance, with hydrogen to form ethane, as shown here. Let's have a look at another type of carbon hybridization, sp2. With sp2 hybridization, the 2s, 2px and 2py mix to form 3 equal orbitals. The pz orbital will stay intact. The angle between the sp2 orbitals is 120 degrees. The sp2 hybridization is used when carbon forms double bonds, for example with another carbon. One sp2 orbital is used for a sigma bond. The pz orbital is used to form what's called a pi bond. Even though the pi bond locks in 2 places, it only corresponds to a single bond. The remaining sp2 orbitals can bind with sigma bonds to other atoms, such as carbon, oxygen, or hydrogen. The bond angle will as before be determined on the angle between the orbitals, and will therefore be 120 degrees. If carbon only bonds with hydrogen atoms, an ethene molecule is formed. Let's have a look at the sp hybridization, the last one for now. In sp hybridization, only the 2s and 2px mix to form 2 equal orbitals. 2py and 2pz stay intact. The angle between the sp orbitals is 180 degrees. The sp hybridization is used when carbon forms triple bonds, for example with another carbon. As with sp2, a sigma bond is formed using one of the sp orbitals. 2 pi bonds are formed with py and pz. The remaining sp orbitals can form sigma bonds to other atoms. The angle between the 2 sigma bonds will be 180 degrees. If only hydrogen atoms are bound to these remaining orbitals, an ethyne molecule is formed. That's it for now. Let's go back to the lab for a little quiz to see if you've got this. Let's see if you understood the essentials of the animation. What is the carbon valence value? Yes. The outer shell of the carbon atom has 4 electrons, so this is its valence value. Interact with it when carbon binds to 4 other distinct atoms. What is the angle of the carbon bonds? Good job. When carbon forms bonds to 4 distinct atoms, it has 4 sp3 hybrid orbitals that are organized forming a regular tetrahedron structure. This means that the angle between each bond is 109.5 degrees. Click the molecules on the holo table to check them out. Interact with the lab pad when you're done. Besides methane, you now see 2 more molecules on the holo table, formaldehyde and carbon dioxide. Note that the red atom represents oxygen. Can you spot the right statement for methane, formaldehyde, and CO2? You nailed it. They all have different bond angles. The bond angles are very important in many reactions in organic chemistry, where they determine the structure of the products. Methane is a hydrocarbon, which means it consists of only carbon and hydrogen. More complex organic compounds contain other elements such as oxygen and nitrogen. Even though CO2 contains carbon, it is not considered an organic molecule, as it does not contain any carbon-hydrogen bonds. As you now know, a carbon with only single bonds forms these at different angles than the carbons with double and triple bonds. Let's explore these differences. Click on the holo table to go back to the center of the room. Go to holo table 1. Your mission here is to build the proposed molecules by adding the hydrogen atoms with the correct angle. New hydrogens can be picked up from the left on the holo table. You can discard excess hydrogens in the trash bin. The molecule can be rotated by clicking the white arrows on either side of it. This way you can get a good view of all the suggested hydrogen positions. Let's see if you can get the correct configuration. Place all hydrogens in ethane at the correct angles. Interact with the lab pad for hints. Good job. Can you do the same for propane? Click on the lab pad for more information. Awesome! Can you do it for propane as well? Well done. It looks like you now know the bond angle of each atom depending on the type of compound. I'm sure you've also noticed that for each extra bond added between 2 carbons there will be 2 fewer hydrogen atoms in the compound. Besides being found in living organisms and their fossils, organic compounds can also be synthesized in the lab. Let me show you a few more examples of where we use them. Click the holo table to go to the screen by the entrance to have a look at some organic compounds. These are some of the carbon-based materials that we use every day. They are used as a source of energy in the food we eat, as fuel for our cars, and to make the water bottles we buy in the supermarket. But these are just a few examples. There are many, many more, and the organic compounds they are made of have many exciting features. Let's check out some important aspects of them. In this picture you can see the 2D structure of two hydrocarbons. Can you spot the difference between them? Well spotted. When representing 2D structures of organic compounds, lines connecting atoms represent bonds. And compound B has a carbon-carbon double bond, which also means it has fewer hydrogens. Compound A is called propane and it's used as gas in many household appliances and as an alternative vehicle fuel. Compound B is called propene and is used as a chemical building block in the industry to produce, for example, surface coatings. Note that in 2D structural formulas like these, we can choose not to take the three-dimensional arrangement into consideration. Now let's explore how you actually give names to these hydrocarbons. Saturated hydrocarbons, also called alkanes, have only single bonds connecting the carbon atoms, while unsaturated ones have double and/or triple carbon bonds in their structure. According to the International Union of Pure and Applied Chemistry, simpler hydrocarbons are named by considering two factors. First, the number of carbons. We use a prefix according to the number of carbons in the molecule. You will find a useful table in the theory section. Let's see if you've got this. What is the name of this compound? Well done. This is the structure of hexane. It's an alkane with 6 carbon atoms. Hexane is one of the major constituents of gasoline. The second basic factor to name a hydrocarbon is based on the types of carbon bonds present in the molecule. We use a specific ending depending on the type of hydrocarbon. Now have a look at these hydrocarbons. Which compound is not present? No. This is incorrect. Please try again. Right again. From left, the molecules are ethene, 2-butene, methane, ethine. Now that you know how to name simple hydrocarbons, let's go use this in a little exercise. Go to holo table 2. Which compound is being shown on the holo table right now? Interact with the lab pad to answer the question. Exactly. 1-butene is so named because it has 4 atoms of carbon. The prefix used is therefore but. Since it has a double bond, the suffix used is -ene. Finally, the number represents the first carbon involved in the double or triple bond. When needed, each carbon can always be assigned a specific number in the structure. In this minigame, we'll see if you can relate 2D structures to the right 3D configuration. A 2D image of a hydrocarbon will appear on the screen in front of you. By clicking the ABC buttons on the holo table, you will see 3 different suggested 3D structures for the shown hydrocarbon. Click the OK button when you think you've selected the correct 3D structure. Are you ready for this challenge? That's not the compound shown on the screen. Remember to have a look at the number of carbons and the type of carbon-carbon bonds. Let's try again. Awesome! You're right, this is propane. It has 3 atoms of carbon that are all with single bonds. Note that all bond angles are the same, specifically 109.5 degrees. Round 2, click the OK button when you think the correct 3D structure is displayed. Bingo! This is 2-butene. It has 4 atoms of carbon and 1 double bond. It's 2 butene and not 1 butene, as a double bond is between second and the third carbon in the chain. Round 3. Nice. You're correct, this is 3-hexene. It has 6 atoms of carbon and 1 double bond connecting carbon 3 and 4, which forms a 120 degrees angle, while the rest of them have 109.5 degrees bond angles. You're doing a great job. What would you like to do now? Besides identifying simple hydrocarbons by their structural or 3D formula, there are chemical tests that help you confirm or discard the type of hydrocarbon you are working with. One of the simplest tests is called the bromine test. It reveals whether a solution contains unsaturated organic compounds, as the bromine reacts with the double and or triple bonds. Do you want to help me with an issue where we'll use the bromine test? Alright. Click on the holo table to go to the wall screen next to the lab entrance. Before we go to work on Simon's issue, you need to know a bit more about organic compounds. There is a virtually infinite amount of them. This is possible due to the existence of isomers and functional groups. Isomers are compounds with the same formula, but with a different arrangement of atoms in the molecule. On the screen in front of you, you can see 2 pairs of isomers. These different arrangements will lead to different properties. We will not focus on isomers in the simulation, but you can learn a little about one type of it if you head to the theory pages. Go to Holo Table 2 to learn the basics about functional groups. What is a functional group then? Functional groups provide the reactivity to the organic compounds, and their position also determines how the compound is named. Here on the Holo Table, you can again see formaldehyde, which contains a double bonded oxygen. That oxygen is a functional group, and when placed this way, the whole compound is called an aldehyde. There are a lot of different functional groups, and some of them contain atoms other than hydrogen and oxygen, such as nitrogen, phosphorus and sulfur. Depending on the arrangement of these atoms, the functional groups are different and provide different properties to the organic compounds. Functional groups are crucial in organic chemistry reactions, and therefore play a central role in the molecules of life. Do you remember the definition of organic compounds? From this image, which compound would you say is not considered an organic compound? You're absolutely right. Even though calcium carbonate contains carbon, it is considered to be an inorganic compound, as it does not contain any carbon-hydrogen bonds. Be aware that a carbon atom can actually change from being part of an organic compound to being part of an inorganic one, and the other way around. When you eat some delicious cake, it contains many different kinds of organic compounds like sugar, fat and protein. When we metabolize these to get access to the energy they contain, we later exhale the carbon atoms they were composed of as inorganic CO2. As you can see, we sometimes don't write the C for carbon and H for hydrogens attached to these carbon atoms. These are called skeletal formulas. The carbon atoms are implied at the corners of the structure. It might look a bit confusing in the beginning, but it is actually really helpful for quickly identifying the important aspects of the molecule. Now, let's get to work on your mission from Simon and see what we can learn about salicylic acid. Click on the Holo Table to go back to the center of the room. Find a glove box and click on it. Put on the safety goggles. Return to the screen on the wall next to the entrance. Salicylic acid is also called 2-hydroxybenzoic acid. It's a compound obtained from the bark of the white willow and wintergreen leaves, but it can also be synthesized in the lab. This is the salicylic acid structural formula. You can see 3 clear functional groups, a hydroxy group in purple, an aromatic group in blue, and a carboxyl group in green. The hydroxy group can be part of different functional groups. When bonded to an aromatic ring as in salicylic acid, the functional group is called a phenol. In Fumba Tooth there is a solution of pure salicylic acid in water, prepared using the pills you brought. You will also find water and hexane, which we will use as negative controls. The positive controls for the respective test will be ethanol, phenol, and acetic acid. You can have a look at the Media tab to see their 2D structure at any time, and check out what it means to have controls in an experiment in the theory pages. Click on the screen to go to FUMA 2. As an extra challenge for you, I did not label the 6 test solutions, so you don't know what is in each beaker. Let's see if you can find the salicylic acid solution and confirm that the pills actually contain the functional groups of this organic compound. You will first test for a hydroxy group using the ceric ammonium nitrate test. The addition of ceric ammonium nitrate reagent to an organic compound with an alcohol or phenol group results in the formation of a dark red color. Alcohols in chemistry are very similar to phenols, but here the hydroxy group is not bonded to an aromatic carbon. According to what you know about the salicylic acid structure, what should happen to that solution after performing this test? Alright. We'll find out if your hypothesis is correct after you've done the experiments. Add each solution from the beakers to a different test tube. Let me help you with the remaining tubes. Add ceric ammonium nitrate to all the tubes. Let me help you with the remaining tubes again. Vortex the tubes and observe the results. Good work. Which compounds seem to have either an alcohol or phenol functional group? Exactly. Those beakers seem to contain solutions of compounds with an alcohol or phenolic functional group. The ceric ammonium nitrate reacts with them, forming a red or brown color. You can have a look at the Media tab to keep track of the results of the experiment. Alright. Now you have narrowed down your options. Let's do a second test to find our sneaky salicylic acid. Go to FUMA 3 on your left. In the second test, you will look for signs of a carboxylic acid group. The addition of sodium bicarbonate to a solution containing an acidic compound results in the formation of some brisk effervescence, as the bicarbonate is converted to water and gaseous CO2. I've already transferred some of the test solutions for you into 6 fresh tubes, so you can get to work. What should happen to the salicylic acid solution when performing this test? Okay. Also, we'll see if your hypothesis is correct after all the experiments. Add sodium bicarbonate to a tube. Nice. Now add sodium bicarbonate to all tubes and observe if anything happens. Alright. Which compounds do you think contain a carboxylic acid group based on this test? Interact with the lab pad to answer the question. Well done. You can see brisk effervescence in those tubes, meaning that they contain a carboxylic group. As before, you can see an overview of the results in the Media tab. Put the spatula back in the beaker. Click the FUMA to go back to the screen on the wall and have a look at the final results. Now that you have performed the experiments, tell me, where was the salicylic acid hiding? You can check the Media tab to have a look at the structures of all 6 compounds again. Interact with the lab pad to answer the question. You are a chemistry champion. Compound A was the salicylic acid, indeed. It's the only compound that gave positive results in both tests, which matches with the presence of a phenolic and a carboxylic acid functional groups at the same time. So now you can confirm Simon that he doesn't need to worry. These pills are safe. Now, let's check how good your predictions were. I have more good news. Both of your hypotheses were correct. You predicted what would happen to salicylic acid in both experiments. Are you the next Marie Curie or Robert Burns Woodward? Well done. You've done a great job. Let me ask you one last question. Looking at the results, can you determine which one is hexane? Interact with the lab pad to answer the question. Brilliant. That's the mindset of a true scientist. You don't have enough data to conclude which compound is hexane. Therefore, you would need to perform more experiments to determine which beaker contains hexane. However, you might have noticed that compound F formed 2 layers in the ceric ammonium nitrate test. This gives us a clue that this might be hexane, as this compound can't be mixed with the aqueous solution of ceric ammonium acetate. I hope you come back another day to complete your training in advanced organic chemistry. We're almost through the simulation now. As a little present, have a look at the 3D structure of salicylic acid on Holo Table 1. Go to Holo Table 1. You know, the pills you brought were just aspirin. Aspirin is also called acetylsalicylic acid, and it's broken down into salicylic acid in your body. For the tests in the lab, I did this conversion for you. Simon can trust his friend. She gave him a very common and effective treatment for simple pains and inflammation. Let's go see how he's doing.
I feel much better now. Thanks for helping me understand my friend's recommendation. Because of your work, I now can stop identifying organic compounds. Today we are using charcoal to light up the barbecue. The meat and vegetables we'll eat contain proteins and carbohydrates. We have plastic bottles for the soda. I wear a nylon shirt. And if I feel bad again, I'll take some more salicylic acid pills. Chemistry is everywhere. I can't wait to learn more about organic chemistry. It's so amazing.